Hello and welcome to everyone to this lecture on violation of assumptions, in which specifically we will talking about the violation of assumption of the no autocorrelation and the specification error. In the last class we have discussed the violation of assumptions of heteroscedasticity and multicollinearity. So we have discussed that once we estimate a regression equation or the regression model, we will get the estimators, that is beta 0 hat and beta 1 hat if it is the two variable regression model. That is, if we have y is equal to beta 0 plus beta 1 x1 plus u, in that case once we estimate using OLS, we will get this parameter beta 0 hat and beta 1 hat. Then the next immediate task we have to examine the reliability of these estimates. For that we have three different criteria. One is the a priori criteria, which basically we derive from the economic theories. Then second we have statistical criteria, and third what we have the second order test or the third criteria, or also it is known as the econometric criteria, in which basically we argue that the statistical properties of the OLS estimates are based on certain assumptions. If those assumptions are not satisfied, then those statistical criteria may not be optimal. Then in such cases, the properties or the statistical criteria which we have used to check the reliability of these estimates may not be appropriate or may not be optimal. Therefore, we go to the second order test, what we know as the econometric criteria, where we do check whether the assumptions is satisfied or not. If not, then what we call the violation of assumptions. And then we basically discuss what will be the consequences if the assumptions are violated, and what may be the cause for such violations, and what will be the way out or what will be the remedy or solutions of such violation. So in the previous lecture we have talked about two such violations. Here we will continue that. Here we will talk about the two other important assumptions and their violations, that is about autocorrelation and misspecification, or what we call specification error. So let us quickly get into it here, what we mean by the assumption of no autocorrelation. So basically, when we say assumption of no autocorrelation, what we mean that the covariances and the correlation between the different error terms or the disturbance are all zero, which we mathematically write in the form of that covariance of ut and us is equal to 0 when all this t is not equal to s. However, when t is equal to s, that becomes variance, for which we have already discussed into the previous lecture. So basically what we mean here that the covariance between, let us say, u1 and u2, or covariance between u2 and u3, or covariance between u1 and u3, so on, all this we are assuming is equal to 0, that is there is no correlation. Then the name autocorrelation has been derived or suggested because here we are dealing with the same variable, different lags, therefore we call the autocorrelation. So when we assume there is no autocorrelation, so basically what we mean that ut and us, that the error terms are independently distributed, which is called serial independence. So there is no dependency, there is no relationship between one lag with the other lag, or in other terms, in other sense we can say there is any absence of pattern in the errors of the regression model. However, when we say there is the autocorrelation, what does basically we mean? We mean that the covariances and the correlation between error terms are not equal to 0, and we say that in mathematical form that covariance between ut and us is not equal to 0. There means there is some kind of relationship between the lags, or in the simple term we can say that in this case when there is the autocorrelation, that what we mean, any error occurred at period time t will have its impact or will be carried over to the next period at t plus 1. So, that means here if you have u1, it has some kind of relationship with u2, and this u2 has some kind of relationship with u3. So, there will be some kind of dependency between u3, u2 and u1, and if we have such kind of dependency and pattern, then here the covariance between u2 and us will not be equal to 0 when this t is not equal to s, and if that happens, then we say there is the problem of autocorrelation. This phenomena is quite common in the time series compared to the cross-sectional data. Why? In the time series, what we do, we basically take the observations of a particular unit across the time, whether it's a firm, whether it's a particular asset. So, in case of time series, we observe the phenomena or the characteristics of any particular variable. It could be, for example, here it could be any return of any particular asset or the performance of a particular firm, so or particular financial instrument. So, let us say if you are taking a firm as an example here. So, if you are observing any characteristics of this firm, let us say here for the time period of t1, for the time period of t2, for the time period of t3, then there is the quite possible, quite likely that whatever we are observing here, that when we are observing the second, those characteristics will be carried over here. So, in the time series, that is why it is quite common, in time series it is quite common to have the problem of autocorrelation, because the characteristics more or less remains the same. Therefore, that could be carried over to the next period, to the next period, or to the next period. So, for example, if you take the GDP in the macroeconomy, so GDP of this year may have impact on the next year, and the next year's GDP to have the next year. However, in case of cross-section data, because we have the different units, the characteristics fundamentals may change across the units. So, therefore, there is quite less likely chance to have the problem of autocorrelation. However, in the cross-section we have the problem of the heteroscedasticity, which we have discussed earlier. So, in the case of time series, we have more problem of the autocorrelation, where in the cross-section we have the more problem of heteroscedasticity. Now, what could be the causes of having the autocorrelation? One of the major issues due to which we have the autocorrelation problem is the specification bias. So, specification bias means the structure of the regression equation which we are using, that may not be appropriate. So, in that case, two category basically we will have, for example, the excluding the relevant variable or incorrect functional form. So, let us take the about the excluding a relevant information. Let us say the true regression equation is y, where it depends on, let us say, beta 0, beta 1 x1 plus beta 2 x2 plus u. So, this is the correct actual form of the regression equation we have. However, while we are estimating, we did not use this, rather than we have used beta 0 plus beta 1 x1 plus u. So, basically what we have done, we have missed out a significant variable which was the part of the which should be the part of the equation, but however we missed that. Now, in that case, the effect of this x2 will be captured by this error term, and if this x2 may have follow a certain process or order. So, now that pattern, that order is being captured by this error term. So, therefore, the pattern of x2 may be reflected in u, and that u1 could be related to u2 and u3 and so on. So, that means we will have the problem of autocorrelation here. Now, let us take the incorrect functional forms. Let us say the true functional form of the relationship is beta 1 x1 plus beta 2 x2 square plus u. However, we have estimated as the beta 0 beta 1 x1 plus beta 2 x2 plus u. Now, in such cases, the effect of x square again could be captured by error term, and that error term may have the pattern of this. So, specification bias, when we omit a significant variable, we may have the problem of autocorrelation, or similarly if we are wrongly specified the regression equation, there also we may have the problem of autocorrelation. The second is the lags or the previous behavior. There is the certain economic phenomena where there will be lag in the reaction. For example, if you are having the investment today, it is not necessary that the effect will become observed today itself, rather than it will take a lag to appear the effect. So, in such cases we do have the problem of autocorrelation. So, any such variable, any such economic phenomena or behavior where we do have the lag behavior, there will may be the problem of autocorrelation. Then the third is the systematic errors in the measurement. So, let us say what we mean by the systematic errors of measurement. Let us say we have equation y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus u. Now, let us say while we are measuring x2, we are making an error. So, that error we could say m1 at time t. Then in the next period, because we are having the same measurement issue. So, for example, let us say it is a faulty machine. So, we are weighing some x2 is the some variable where we needed the weight. So, we are weighing every time. So, in the first observation we made the error m1, the next observation again we will make the same error, let us say m2, similarly m3. But what will happen with this? All this error will be accumulated with the error term. Now, for the error term here, it will be for this m1, and at time 2 what will happen? This error term will have now the measurement is of m1 plus m2. Similarly, for u at time 3 what will have m1 plus m2 plus m3, so on. So, let us say un, so it will be m1 plus m2 plus m3, so on, plus mn. So, now this have a systematic pattern in the error term, and this systematic pattern is basically reflects the presence of the problem of autocorrelation. And the fourth is the non-stationarity, which we basically will be discussing in this course very extensively, and it plays very an important role, particularly in the data of the finance. So, when we say non-stationarity, basically this mean variances and the covariance changes over time, and basically that has the problem of autocorrelation. So, we will have a detailed discussion on the concept of non-stationarity and its impact, and why we have to resort into the different tools and techniques. That is basically a quite extensive part of this course on financial econometrics. So, the fourth issue due to which there may be the presence of autocorrelation is the non-stationarity. Now, if we have this, how it can going to impact our OLS estimates? The first point, this OLS estimators is linear, consistent and biased, but it will be blue. That is, it will be linear, it will be consistent, it will be unbiased, but it will not be efficient. So, the standard error of the regression coefficients may seriously underestimate the true standard deviation of the estimated regression coefficient. When there is autocorrelation, this T, F and the chi-square test are basically not valid. We will not have an appropriate interpretation here. Now, this autocorrelation could be grouped into the two, or could be categorized into two, that is the first order and higher order autocorrelation. So, basically to understand that, let us consider we have a regression equation yt, which depends on the variable k explanatory variables, and we have the error term and an intercept term beta 0. Now, if we have the functional form of the autocorrelation as ut equal to rho ut minus 1 et. So, basically ut depends on ut minus 1. Here the rho is basically what we call the correlation coefficient between ut and ut minus 1, and the linear regression, it is nothing but the slope coefficient what we have. Now, if that is the case, then this is called the first order autocorrelation. Why we call the first order autocorrelation? Because there is only one lag term of ut which affects the current ut. However, if we have a functional form ut is equal to rho ut minus 1 rho to ut minus 2 and so on, let us say up to order p, then what we call the autocorrelation of higher order, or here in this specific case what we call the pth order of autocorrelation, because the current observation of error term depends the p legs of error term. So, in short, if we have only one lag in this, then what we call the first order autocorrelation. If we have more than one lag, that is the more than one previous error terms is affecting the current error term, then we will call the higher order autocorrelation. Now, order of autocorrelation depends on the lags of the error term basically here. Now, let us talk about here this, let us consider this first order autocorrelation term. So, rho is the parameter measures the strength of association between the ut and ut minus 1, and here the et is the basically the error term which follows a normal distribution. Then here the rho is known as the first order autocorrelation coefficient and lies between minus 1 and plus 1, and we have three scenario, that is if rho is equal to 0, that means there is no autocorrelation, ut is IAD, so there is no problem of autocorrelation. However, if rho is moving towards plus 1, then the value of ut depends on ut minus 1 and we have positive autocorrelation, and if we have rho minus 1, again there will be a association between ut and ut minus 1 and we will have a negative autocorrelation. So, however, we have negative autocorrelation here. So, that you can see here in the graphical form. So, when we say, so basically here we are drawing that the relationship between of ut and at time t, and if we are following a certain pattern, that means there is the problem of autocorrelation. If there is no pattern, then that means there is no autocorrelation. So, here basically what we are observing, there is the positive autocorrelation, then it is coming back and so forth, and here we have the rho is equal to basically positive. So, there is the positive autocorrelation, here we have rho is negative, that is basically negative autocorrelation. So, here basically we have the fluctuating here. So, this is the sum. So, in all four cases what we are observing, the error term follows a certain pattern. If it is following the pattern, that means there is the presence of autocorrelation. Now, what will be the consequences? So, if we have the problem of autocorrelation, then what will be the consequences we will have? So, the first consider this, then if ut correlated, then we will have the problem that OLS estimates of betas will be unbiased and consistent, and OLS estimates will be inefficient, that means no more blue. Third, the estimated variance of the regression coefficient will be biased and inconsistent. Fourth, in most cases what we will have, R square will be overestimated and T statistics will tend to be higher. So, from here we get another very important aspect, what we have discussed in the previous classes, that R square we use to pick and choose the comparative models. So, if R square is high, that model fits well, that is what we have discussed. That means higher R square is a desirable property of the regression equation. However, we have to be very cautious if we have the high R square and also the high T, because from here the problem of autocorrelation we can observe that when we have the problem of autocorrelation, what will happen, R square will be high and the T statistic will be also high. So, it may not represent the true relationship, rather than due to the presence of autocorrelation we may have the high R square as well as the high T statistics. So, therefore, whenever we are using this R square, we must cross check it using the second order test or econometric criteria. So, this situation emphasizes that why we should be concerned about the second order test, that means why we should be concerned about the validation of the assumptions. So, in specific to this case, the R square could be high as well as the T statistics could be high. So, basically giving uh, a desirable property which we wanted to have in any regression model. However, that could be due to the presence of the autocorrelation, not because of it is a good estimate model we have. So, whenever we have to use this linear regression model, we have to careful about the assumptions. Now, how to detect that autocorrelation? So, there are the two broad groups. So, that is one, the first informal done through the graphs and therefore called the graphical method. Second, we have the through formal test such as Durbin-Watson statistics, Bruce-Godfrey test and the Durbin's edge test. So, basically this is for we will talk about that in detail. So, in the graphical method, basically what we do, we draw the error term and across the time. So, if we find any pattern, that means there might be the presence of the autocorrelation. So, one way, draw the UT across the time, or we can draw UT and UT minus 1. Again, if there is any pattern, then we will have the problem of autocorrelation. Now, remember this UT are the error term which is not observable. So, instead of UT, what we use the UT hat, and here we use the UT hat and UT minus hat. So, basically which is nothing but the estimated error terms, or what we call it residuals. Though we wanted to know the pattern about the error terms, but because it is not available, so what we use the estimated value here. So, that is about the graphical method. Then the second method is the formal test, or the Durbin-Watson statistics, Bruce-Godfrey test and the Durbin's. Out of these three, so primarily the Durbin-Watson test is widely used and known. And the Durbin's test is basically nothing, but we will see there is the limitation of the Durbin-Watson test. That limitation that we cannot add the lag terms of the dependent variable. If you are adding, then we cannot use the Durbin-Watson test statistic. So, to correct that, we have the Durbin's H test. So, that is the basically difference we have between the Durbin-Watson test and the Durbin's H test. Durbin's H test basically for the presence of the lag dependent variable as a regressor or as a independent variable. Now, what is the Durbin-Watson test we have? So, this test is applicable when following assumptions are satisfied. First, the regression model includes a constant term. Second, autocorrelation is assumed to be the first order only, not more than that. Second, the equation does not include the lag dependent variable as the explanatory variable. If these assumptions are satisfied, then only we can use the Durbin-Watson test. So, here consider this particular equation. So, here and we have the first order autocorrelation is UT in this. Then to test the presence of autocorrelation of the first order, the null alternative hypothesis are this: rho is equal to 0 and rho is not equal to 0. So, if the rho is equal to 0, that means there is no autocorrelation. If the rho is not equal to 0, that means there is the presence of autocorrelation. Now, when we say rho is not equal to 0, that means it could be positive, it could be negative. Then basically what we do to conduct Durbin-Watson test statistics, what we do first estimate the model by OLS and obtain the residuals. Then the second step, calculate the DW statistics. How we calculate that? Using this particular formula here. So, once we calculate then we will make use of step 3 following table. We will make use of this following table. So, what is the basically following table? Let us understand here. So, in the step 2, we calculate the Durbin-Watson statistics using this particular formula. So, once we have estimated that, then to make the decision we use this particular table. So, what this particular table says that if the Durbin-Watson statistics is basically in between these two regions, so we have no autocorrelation. That means we have the two limits critical limits, namely as the upper limit and the lower limit. So, if the autocorrelation is between this upper limit and the lower limit, that is the value of this D statistics, that means there is no autocorrelation. However, if it lies between this lower limit and the upper limit here, we cannot make any decision. Similarly, here if it lies between this lower limit and the upper limit, we cannot make any decision. However, if it is more than this upper limit, that means there is the positive autocorrelation. If it is here, then we will sorry, it is negative autocorrelation. If we here, then it is positive autocorrelation. So basically, let us say what we have. So step 4, the two case we have the positive and negative autocorrelation. So to test for the positive autocorrelation, what we have to do this. On the other hand, for the if the d is less than equal to the lower limit, that is this, reject the null hypothesis and conclude that there is the positive correlation. Now, if the d is more than or greater than the upper limit, this, that means you accept the null hypothesis, that is there is no autocorrelation, we have problem. Now, if the d statistics is, so here we can observe that the first case what we do for test for the positive autocorrelation, in that case we have the null hypothesis equal to 0, alternate is rho is more than 1, and how we do that. If the calculated d statistic is less than or equal to dl, so this case then reject the null, that means there is the positive autocorrelation we have. However, if the d is more than this, that means you accept that null, that is there is no autocorrelation, positive autocorrelation. Similarly, if the value of d statistics lies between the dl and the du, that means there is the inconclusive decision, we cannot say whether there is the problem of autocorrelation or not. Similarly, here we have in this case where we have the negative autocorrelation. So, for the negative autocorrelation, what we have, again the null we have, there is no 0, rho, the value of rho is equal to 0, and the negative we have the value of rho is less than 1. Now, if the d is more than 4 minus dl, this, so if it is more than this, that means if it lies in this area, then we will reject the null and we will conclude that there is the negative autocorrelation. However, if the d is less than this, so that means if it is lies in this area, then what we call there is the accept the null, that means there is no positive negative autocorrelation we have. Then if it is lies in between these two limits, that is in this zone, that means there is the test is inconclusive, we cannot say what is the there is the presence of autocorrelation now. Now, let us give you a very what we known as the rule of thumb, very easy to decide whether the there is the presence of autocorrelation or not. So, that rule of thumb basically is this: if we have this value, then because ut hat are generally small, then we can modify this equation and we can write is d is equivalent to 1 plus 1 minus this particular equation here. So, in that case we also have that rho is basically this particular value here. So, that means we could write here in simple terms this, that the value of d will be equivalent to twice into 1 minus rho here. Now, if this is the case, then what we have, since rho is lies between plus 1 and minus 1, this rho is correlation coefficient between the ut and ut minus 1 or ut minus 1 and ut minus 2. So, now if this rho lies between more than 1 and less than 1, that means there is the problem of autocorrelation. If that is the case, therefore, this d will lie between more than 0 or less than 4. So, it implies that if the value of d is more than 0 and less than 4, that means there is the problem of autocorrelation we have. Now, so what we can note here, if rho is equal to 0, then d is equal to 2, that means there is no autocorrelation. If rho is equal to 1, then d is equal to 0, that means positive autocorrelation. If rho is equal to minus 1, then d is equal to 4, that means negative autocorrelation. So, that means instead of the upper limit and lower limit, here we can rely on these statistics. That is, if the value of d is equivalent to 2, that means there is no autocorrelation. So, we can conclude there is no autocorrelation. If the value of d and basically moves equal to 0, that means there is the most probably a positive autocorrelation. On the other hand, if the value of D is equivalent to 4, that means there is negative 1, that means there is the negative autocorrelation. So, based on this we can make easy decision about the presence of autocorrelation. However, there is a certain shortcoming we have, that is maybe inconclusive, then what we will make the decision. Second, not applicable when the lag dependent variable is used as the explanatory variable, cannot take account of the higher autocorrelation. So, in such cases we can rely on the Bush Godfrey test, or we can use the arch test, or we can use the other different test statistics are there. So, what are the remedies we have? So, analyze the type of autocorrelation. First, we have to see what kind of autocorrelation we have. If do we have the pure autocorrelation, or we have the autocorrelation error due to the misspecification of the model. Pure autocorrelation by structure of the data we have. So, if that is the case, then we can use the generalized least square method. However, if we have the autocorrelation due to the misspecification, we can correct those misspecification, and by correcting those misspecifications we can remove the problem of autocorrelation. For example, let us say if the autocorrelation is arising due to the omitting of variables, so we can include that variable and we make the correction. So, there is the another methods we have, the naive Bayes method for the estimation we have, or we can continue to use the OLS method. For example, if you have the very small sample, then we can use, because in the smaller sample there is high likely chance there may not be the problem of autocorrelation, because it is the phenomena of the time series. So, then we can use this OLS method here. Now, let us talk about the second violation of the assumptions, that is the specification errors, or what we call the misspecification. Because we may you may recall that one of the assumptions we have in the OLS, that the equation is correctly specified. If it is not specified correctly, then what will be the consequences? Let us discuss those. So, basically when we say misspecification, so it could be, for example, omitting the influential variable. So, consider this population regression function here. So, in the true population, the beta 1 is not equal to 0 and beta 2 is not equal to 0. That means both x1 and x2 has important significance on y. Now, let us say if you are estimating here y is equal to beta 0, beta 1, x1 plus u star to make the differences here. Now, in such case, so the true relation is this and we are estimating this, then in that case what will happen here? X2 is wrongfully emitted, then the error term of this equation will be u star equal to beta 2 x2 plus u, because this particular pattern here now will be captured by this error term. Now, let us see the certain properties of the error term of here. Now, the expectation of this error term, that means expectation of beta 2 x2 plus u, then expectation of beta 2 x2 plus u. So, this could be the 0, but this is not equal to 0. That means the assumption of that expectation value of error term is equal to 0 is here in this case is not satisfied. Now, the assumption that error term has 0 mean is now violated. Furthermore, if the excluded variable x2 happens to be the correlated with x1, then the error term is no longer independent of x1, because the effect of x2 is coming to the error term and the x2 has the relation with x1. Therefore, via x2 the error term has the relation with the explanatory variable x1, again the violation of assumption. So, this results in estimators of beta 0, beta 1 to be biased and inconsistent. So, this is called omitted variable bias. Now, let us take the second case where we are including the non-influential variable. Let us say the correct model is this, but however we are estimating is this. So, as x2 does not belong to the correct model, its population coefficient should be equal to 0. If we are testing and able to find that beta 2 is equal to 0, then we will drop, then not an issue. Then none of the assumptions violating, all estimators are both unbiased and consistent. However, OLS estimators will be unbiased and consistent if this beta 2 equal to 0 here. Now, let us say in this case, however, it is unlikely that happen. If x1 is correlated with x2, then the additional unnecessary element of multicollinearity will be introduced. A higher standard error of the coefficient of x1, the value of r square will fall. Now the sign of other coefficient remains the same, the magnitude does not change. T statistics of other respective variables will not be affected appreciably. However, a strong correlation may change this dynamics. If there is this very strong relationship between x2 and x1 and x2 we have included irrelevant, then the correlation between these two we may have the problem. As such, x2 may not have the problem, because in that case beta 2 may be appear to 0. If the beta 2 does not appear to equal to 0, and it may not have as such impact. However, if there is a strong correlation between x1 and x2, that may create the certain issue with the OLS estimates. Now, if let us say we are doing both, we are omitting the important variable and including the irrelevant variable. In that case, what we will have, we will making the double mistake. So, omitting relevant variable leads to bias inconsistent estimates, where the inclusion of non-influential variable cause the inefficient estimate. However, omitting is the more serious issue compared to including the non-influencer variable. Now, what is the solution? Variable is omitted due to the non-availability most of the cases. Why we are not able to include? Because that may be that the data is not available of that. For example, consider a model of this. So, we are considering that here this model. A model where the monthly salary of an individual is associated with whether he is male or female, whether he has spent, how much years he has spent in education. Both the factors can be quantified and included into the model. For example, we can capture the education due to how much, by including how much he has spent time on that. Gender we can obviously include. However, if you also assume that the salary level can be affected by the socio-economic environment in which each person is brought up, these are the two. However, how will capture the socio-economic variable? So, it is hard to have a quantified measure. So, in that case, we have to drop that particular variable here. Now, not including the background variable in the model leads to the biased estimates of beta 1 and beta 2. So, that means it is not showing a true picture. Now, let us say the main aim here, the goal was basically to get the appropriate estimates of those two coefficients here. Then we are not so much concerned about the beta 3. Then what we can do? We can take a proxy variable of the omitted variable. Let us say we are taking the family income. We know that the family income cannot represent the true picture of the socio-economic background. However, if we are not including, we will have the bias estimates of beta 1 and beta 2, which is the basically primary concern we have. But if we are including the family income, which may up to some extent may represent the socio-economic background, by including that, basically we are correcting the beta 1 and beta 2, which is the basically primary concern we have. So, by including that, we will make this solution. So, what we will basically do is unobserved, we know that x1 this. So, we estimate this value here and this. So, by estimating this model, we do not get unbiased estimates of beta 1 and beta 4, but unbiased estimates we get estimates of A1, beta 2, beta 3 and A4, and we are concerned with this. We are not primarily concerned with the beta 1 and beta 4. So, therefore, in such cases we can depending on the situation, depending on what are the objective we had, we can take the proxy measures and we can include the omitted variable into the regression equation. The sources of the specification errors may arise when the incorrect functional form is included. Let us say what we have this two regression equation, we are estimating this log form here. So, the parameters beta 1 and gamma, beta and gamma is nonlinear model represents the elasticities. In the linear model, beta shows an estimate of the change in y after a unit change x3 and so. So, beta and gamma are incorrect estimators of the true population parameter. So, if it is in this form and we are estimating in this form. So, in this form the beta represents the elasticities, gamma represents the elasticities. However, here in if you are using this linear regression model, that means this beta and gamma is representing the unit change. So it entirely changed the relationship. So that is the basically what we call the wrong functional form. So what we have to do, we have to check the residuals in these cases. The choice of the functional form plays an important role. Thus, we need a formal test for comparing the alternative models functional form. We have the same dependent variable. Things are easy. Estimate both models and choose the one with the higher R square. However, if the dependent variables are different and immediate comparison is impossible, we use the Box-Cox transformation. So basically, in Box-Cox transformation, what we do? Let us assume we have these two models here. We have one, we have the simple linear regression model. Here we have the log and log model. So in these cases, we need to scale the y variable in such a way that we are able to compare these two models. So the procedure to do this. So basically, we have to scale up these two variable, this y and the log y, in such a way we can compare these two. So to do that, we use the Box-Cox transformation. So basically what we do in the Box-Cox transformation, in the first step, obtain the geometric mean of the sample values. So here we obtain the geometric mean of the sample values here. Transfer the sample y values by dividing each of them by the obtained geometric mean in the first case. So here y star is nothing, the original yi divided by this geometric mean of this sample observation. Now estimate both the models y star as the dependent variable. The equation with the lower RSS will be preferred. So to check whether it is significantly better, calculate this statistic and check with the chi-square distribution. The lower is the one is the with the lower will basically making the choose here. Then the measurement error may also create the problem of misspecification. So sometimes data may not be measured appropriately. So in that case, measurement either in the dependent or explanatory variable or both. Consider this particular example here. Observe the value of y is this, y and y star. So y star is, let us say, this. So this is the true, but we are observing this y star which has the flaw that y star is nothing but y plus w. This w is the basically measurement error if we have. To estimate the model, we use this y star minus w here. Now if we have this case, we will have the problem. So what is the solution we have? That we use this model, we use y, where we basically, if we know the measurement error, we deduct that from the y star, then we estimate this, then it will be correctly specified regression model. So today basically we have talked about the violation of the two assumptions, that is the problem of autocorrelation and misspecification error. So now we will talk about So in brief today what we have talked about the problem of the autocorrelation, and we have talked about the misspecification. So we discussed about what are the regions of autocorrelation, how to detect that, and what will be the remedial measures. Similarly, we have talked about the misspecification. It's in certain cases how we can solve those misspecifications. Thank you so much. See you in the next class.